welcome back. In the last video we have seen a review of complex function theory up to the point where we have seen the Cauchy residue theorem. If you have an analytical function in some domain D except at some finite number of singular points can be poles of simple poles, that means it is like 1 by z minus z naught, or pole of order m, that is like 1 by z minus z naught power m. So, z naught is, in this case z naught is a pole of order m, otherwise it is essential singularity. That is why if you look at its Laurent series, that means if you consider the neighborhood of z naught, if you make a suppose z naught is the singular point, in the neighborhood of z naught within that disk except that point z naught, you can have some series expansion. That is a Laurent series, that is a theorem, it is called, you can look into the book, complex function theory book, for example Churchill, where you can find, you can have an expansion for f of z in terms of z minus z naught powers, both negatives and negative powers and positive powers of z minus z naught. That means 1 by z minus z naught and z naught power m, or z minus z naught power m. So, where m is positive number, so positive integer. So, that way you can have such a Laurent series expansion. In the, if you have a negative, you have infinite number of negative powers, you say that singular point is essential singularity. For example, e power minus z square 0 is you will have a 1 by z square, e power minus 1 by z square, or e power minus 1 by z. If you look at it has all the negative powers. So, 0 is essential singularity. Okay. E power 1 by z, for example, if f of z is e power 1 by z, then you have this infinite negative powers. So, 0 is essential singularity. So, we will see in this video how we can evaluate certain real integrals which are improper integrals or usual integrals. How do you make use of this Cauchy residue theorem to evaluate these integrals. So, let me start with this. What kind of integrals you can evaluate? What type of integrals? What type of integrals one can evaluate using this complex function theory or Cauchy residue theorem. So, for one simple thing is, if you have anything from 0 to 2 pi integrals and some kind of a rational function of both sin theta and cos theta, and if you have d theta, if you have something like this, what we do is, so you have a rational function of sin and cos theta. So, what I do is I consider z as 0 to 2 pi. So, I consider z as e power I theta as a unit circle. Unit circle I can represent like 0 e power I theta, theta is between 0 to 2 pi. So, the idea is to make this kind of integral as over a unit circle. For example, unit circle is mod z equal to 1, a closed curve. So, this is over this 0 to 2 pi, I make this, and real part of sin theta. So, in this sin theta is z plus z bar by 2 is cos theta, and then z minus z bar divided by 2y is sin theta. So, you simply substitute r of sin theta as z minus some other function r tilde of z and z bar. What is d theta? dz is I times e power I theta d theta. So, e power I theta d theta, e power I theta is z. So, you have I z d theta. So, d theta you can replace with dz by I theta, I z. So, once you have this, you look at this function as your integrand over this closed interval. So, you see that z equal to 0 is a singular point, 0 is a singular point. So, for which you calculate, this is a 2 pi I times a residue of if 0 is the only root, you calculate this residue of the whatever the integrand, residue of the integrand at z equal to 0. If this is the 0 is the only point, if this rational function is having some other singular points which are inside this unit disk, or unit circle. Within the unit circle you have to find those residues, sum of all the residues. If I assume that 0 is the only 0 is the only singular point, because 1 by z r tilde of z bar, if it does not have, if it is an analytical function, so you can have this residues. This is the integral. So, this is the value of the integral for this. So, this is one such type you can calculate. So, what is the meaning of residue? How do I find this residue? Let me calculate. So, if once you have this f of z as a Laurent series expansion, as I explained, if you look into the textbook you will understand that if you have f of z, if there are three types of singularities. One is the removable singularity, that is not a singular point, is like sin z by z. If you look at this, it is defined as a function of f z is a function is defined for every z not equal to 0, okay, which is analytic at every point which is z is not equal to 0. At z equal to 0, what happens? Z equal to 0, this limit of f of z as z goes to 0 is limit of sin z by z. Just like usual limit, if you calculate, is 1. So, if you define this as a function as 1, then this is a analytical function, okay. So, you can remove the singular, there is a 0 is not a singular point. If you define it like this, 0 is not a singular point. So, this is such a singular point is called a removable singular point, that is not of our concern. What we have is, if it is a pole, you can get the Laurent series expansion, like if it is z naught is the pole for this function, you can get this as some c minus 1 z minus z naught plus c naught plus c1 z minus z naught and so on. You get something like this. This is the expansion in the neighborhood of z belongs to the neighborhood of z naught. This is valid, okay. This is how you can get the expansion Laurent series, and then c minus 1 is a residue of f of z at z equal to z naught. So, in general, without expanding this, you can calculate what is that. So, what is from this, suppose you have this form, what is this C1? C1 is actually z minus z naught into f of z. You consider this limit z goes to z naught. So, this is exactly, if you multiply this, what you get is limit z goes to z naught, z minus z naught into c minus 1, that is going to be c minus 1 plus c naught times z minus z naught plus c1 times z minus z naught square and so on. So, as you see, this is going to be c minus 1. So, this is exactly our residue. So, if you calculate this is you can easily calculate this limit than expanding a function as a Laurent series and looking at its powers of z minus z naught, okay. This is how you find if it is a simple pole, that is a pole of order 1, if you have, this is how you calculate the residue. So, this is the expression. So, you use this one to calculate the residue. If it is for example, if you have a pole of order 2 or in general pole of order 1 by m. So, what you have is, suppose if it is a pole of order 2, let me do. So, you have some constant times, Laurent series will be like this. So, but what you require is only c minus 1. So, c minus 1, what you do here is, so if you want to calculate c minus 1, to get that c minus 1, I am just removing it here and do. So, we are looking for c minus 1. So, what I do is I calculate f of z times I multiply z minus z naught whole square, okay. If I do this, c minus 2 plus c minus 1 into z minus z naught plus c 0 times z minus z naught square and so on. So, how do I get my c minus 1 is simply differentiate d dz of f of z times z minus z naught whole square. If I do this, if I differentiate, I get my c minus 1, okay. And then so this is exactly my c minus 1. I differentiate this. Suppose if I have a 3 here, so if I have m in general, c minus m, and in between I have terms which are up to c minus 1. So, still I am looking for c minus 1. What I do is I multiply c z minus power m. So, you have a c minus m, c minus so you will have terms like this up to here, and you have here c minus m minus 1, okay. So, you have to differentiate this up to m minus 1 terms. d power m by d z power m minus 1. So, that is exactly your C1, right. So, this one, and then you take this limit z goes to z naught. Limit z goes to z naught, if you differentiate and take the limit z goes to z naught, all other terms will become 0. You differentiate m minus 1 times, and then you can get your C minus 1, other terms will simply become 0. Okay. So, bigger terms if you do, still the z minus z naught terms will be there or 0. So, z minus z naught is there, you are anyway taking the limit z goes to z naught, those are all becoming 0. So, except only this contribution will be C minus 1, that is exactly your residue. So, if you have a function f of z which is having a pole at z naught of order m, you calculate. So, what you get is if you differentiate m minus 1 times, you get m minus 1 factorial here. So, 1 over m minus 1 factorial, if I divide this side, if I bring this side, I get this one. Okay. So, C minus 1 is 1 over m minus 1 factorial times, you calculate this limit. So, here I have power m. Okay. So, you multiply, so f of z times z minus z naught power m, you for this you differentiate m minus 1 times and take the limit z goes to z naught, that is exactly your residue. So, this is how you calculate. If it is a pole, how do you find the residue? So, if it is essential singularity, if so happen that if your integrand is essential singularity something like 1 by z, you do not have choice 1 by z or z square, you get the exponential expansion. So, 1 plus 1 by z square by 1 factorial and so on. Okay. 1 by z power 4 into 1 by 2 factorial and so on. So, what is the coefficient of 1 by z? That is 0. So, there is no 1 by z coefficient. So, the residue of this function at z equal to 0 is actually 0, because 1 by z coefficient is not there. If I have 1 by z, this will be 1 by z. So, in this case you have 1 by z square and so on. So, in this case 1 by z coefficient is 1. So, you have residue is 1 for essential singularity at z equal to 0, if your function is having essential singularity. So, basically you have 3 types of singularities: pole, simple pole, pole of order m, or essential singularity. So, in all these 3 cases you can find residue, which you can use to evaluate your integrals here. So, if you these kind of simple real integrals, okay, integral 0 to 2 pi rational function of sin theta cos theta, if you have, you can evaluate, and that is first type of simple integral. A second type is you can evaluate some improper integrals. For example, I am not giving I am just giving you I am not giving you any example to do here. So, you can look into the book and see the example how to do in this case. Second type of integral that we can evaluate is improper integrals. For example, minus infinity fx dx. So, this as a definition, we have seen that this is actually r goes to infinity minus r to r f of x dx. This is an improper integral. So, we can evaluate such integrals by considering f of z dz over a closed curve gamma. Okay. What is that gamma? Exactly, to evaluate this type of integrals, we can evaluate like this. This is if we consider something like this, if you can get like this. So, this is minus r to plus r. So, this is the integral, this is the contour you get, this closed contour you try to get. This is a semicircle like this. If you can if you use this semicircle as your contour gamma, by considering this is actually you have seen, because if f of z is analytic except at finite number of poles inside, then this is actually 2 pi I times the residue of f of z at all the poles at z equal to z I. So, I is running from 1 to, so let us say g j is from 1 to n. So, n where zj belongs to inside gamma. Okay. So, this is so this way you can do, but then what happens to the left hand side where this is coming into picture. So, you if f of z is of order of like 1 by z square. So, that means you take this z square, multiply and take the limit z goes to infinity, and this is going to be constant if this is a constant, or for example, f of z is like 1 over z square plus 1, or z by z cube plus, or z power 4 plus 1. So, you see this is the order of 1 by z cube. If it is z square z cube, this is order of z square. If it is 1 by z square, it is order of z square. Okay. So, such a functions if you consider, you can easily show that by just considering the parameterization over this semicircle, one can show that this integral left hand side will be, if f of z is such that this is the order of 1 by z square, that means this, then this left hand side we can write this as integral over one integral is minus r to r f of x. So, here we are on the real line. So, you have f of x dx. So, that is exactly what you want, plus other integral that is over a semicircle. So, semicircle if you call mod z is, so semicircle. So, how do I put it? So, see if you call this semicircle as C, let me call this CR. CR is my semicircle, only this part, upper semicircle. If I write like this, C over CR, now you are in the complex plane, you have to write f of z dz. If f of z is such that this, I can show that this is actually, this goes to C capital R here, actually here, okay, is of radius r from 0 origin. So, this you can show that this goes to 0 as r goes to infinity. So, this eventually this will become 0 as r goes to infinity, this goes to minus infinity to infinity f of x dx, and this is right hand side nothing to do with r. So, this is as it is 2 pi times sum of all the residues. Okay. So, this you calculate, you can easily calculate for the given function f, if f is of this form, and the left hand side is becomes this is exactly what you require. So, this equal to this. So, if you know all the residues of this function at the singularities inside this closed curve, that means you know the value of this integral. So, this is how you calculate this function, this integral, these kind of improper integrals. I am just giving you briefly idea how you can getting a. So, if you really want a complete picture, you can look at the technicalities of this in the textbook. So, let me see the other type. Other type you can easily see is using if you have minus infinity to infinity, and if you have a px by qx, these are the polynomials. Let us call this, these are the polynomials of minimum. So, here I have chosen fx. Fx is such that order of fx is like 1 by z square. Okay. That means numerator is, what exactly this means is f of z is p of z divided by q of z, where p z qz are polynomials, but minimum degree of q is more than or equal to 2. So, minimum degree of q is actually equal to degree of p plus or greater than 2, greater than or equal to 2. So, degree of q minus p, or rather how do I put it. So, degree of p is smaller than degree of q is more than or equal to 2, more than 2 of degree p. Okay. So, if it is z here, you should have z cubes here, okay, 2z plus, this is the order of 1 by z square. This is the form, this is the meaning of this. Okay. But if it is not like this, if you have some oscillatory functions like e power, if you have e power I, for example cos x or sin x, cos tx or sin tx, okay, or let me put it like e power I I t x, I some let us say a x, a is a constant, a x dx. If you want to evaluate this, if you want to use the same kind of technique, same contour, what you need is degree of q of x has to be equal to it is more than is equal to 1 plus degree of p, degree of p, degree of p of x. This should be 1 more than a degree of p. If you have then this is then then you can apply this same technique using this. What I do is, in this case, to evaluate this integral, I consider over this contour minus r to r, and this is like gamma. So, you same way you can calculate, gamma is the closed curve, and if you call this as C capital R as a semicircular arc. So, you consider this over gamma, the closed curve, this P of z by Q of z times e power I a z dz. So, you consider this integral, and this is minus r to r px by qx times e power I a x dx, if it is on this, plus the other integral, that is over C r p of z by q of z and e power I a z. So, over this semicircular arc, one can show that this goes to 0 as r goes to infinity. Okay. So, this goes to what you require. So, as a integral what you want, and this is actually equal to this, and which is by Cauchy residue theorem, you have 2 pi I times all the residues again of this p of z by q of z times e power I a z for this function at all z j j, all these z j j's are inside, and you take the sum, j is from, if they are n, and you take the sum of all of them with multiplication with 2 I. And if q of z is having a singular point here, you indent it with a contour like this, so that you contour like this you take. So, you look at this one. So, this contribution here will give you some other things. So, that is going to be this one plus pi I times, or I think minus or plus. So, there will be contribution here. Okay. So, you have to consider this contour, and then look at the same way on the small piece, it is a contribution, this integral will be 0, but here this is going to be that is going to be. So, in that case you call this it is a cut, you are actually removing this point. So, equally you are going from, if it is a 0. So, such a thing is called principal value of the integral. Okay. So, let us not bother, those kind of things are not required here. So, if you look into this this kind of techniques, this is how you pick up proper contour, closed contour, and look at the proper integrand as a complex function, and so that your integrand comes into the picture over a real line, and other part you should be able to make it 0 as r goes to infinity if your integrand is sufficiently behaves if your integrand behaves sufficiently sufficient conditions. For example, here is this one, earlier you have this is the condition. Okay. So, if this is satisfied, you can actually get this integral using this Cauchy residue theorem. So, this is how you can get, there are many other things. For example, when you have roots, q of z is having a real roots here, you cannot allow this contour, because this is on the contour you have a singular point. As you see Cauchy residue theorem in the earlier video, you have to see that if it is f of z is analytic in D except at this few points in D, and gamma is inside D. So, gamma, so if you look at z0, z1, zn are the singular points inside gamma, but not on gamma. Okay. So, it is like inside gamma and all these singular points, and you are looking at the integral over this contour gamma. So, here also if you can, but if you have a q of x is having a root here, you cannot do that. In that case, you take the indentation like this or like this, whichever way you can take, and then evaluate over this, so that you are at finally this is let us say epsilon, you allow epsilon goes to 0. So, over this you calculate as epsilon goes to 0, the contribution of this, that may be 0, and the contribution here that makes it here, you are actually removing this point equally. So, that is a kind of a singular, that is, in that case what you get this integral here is, as r goes to infinity, epsilon goes to 0, you have a cut integral, that is the Cauchy principal value of the integral. So, you remove this point, you look at the integral. So, Cauchy residue, Cauchy principal value of the integral is, if you want to calculate Cauchy residue value of let us say 1 by x around 0, you consider integral from minus 1 to 1 if you want dx. This as such it is not integrable, because 1 by 0 is the singular point. If you cut it, then you have a Cauchy integral value this is, how do I do it? This is like 1 minus 1 minus epsilon 1 by x dx plus epsilon to 1 1 by x dx. You look at this way. So, you remove this point 0, you cut it as from minus epsilon to epsilon, and finally you allow epsilon goes to 0. So, this limit as such may exist. For example, this is log minus epsilon minus log minus 1 plus log 1 is 0 minus log epsilon, this minus log epsilon. So, log epsilon if you cancel it with, of course, log minus, so you get that contribution will be e I pi minus log minus 1, something like this. So, this limit will exist as a, if this limit exists as epsilon goes to 0. Okay. I am not doing the calculations here. If this limit exists, you say that principal value of this integral exists. That is what exactly you will get if you have a roots here. Okay. So, such integrals, so your improper integrals will be Cauchy principal value of the integrals if you have a singular point on the real line. So, those integrals you will be evaluating by the same technique if you have a singular point here. So, in that case this I becomes Cauchy principal value of integral if qx is having a real root, but the technique is same. So, this is just one of the a glimpse of how you apply Cauchy residue calculus, Cauchy residue theorem to evaluate some real integrals, which are simple integrals, finite integrals, that is 0 to 2 pi type of integrals, or improper integrals where the integral from minus infinity to infinity also, or from 0 to infinity also you can do, but you have to properly choose your contour. If you want 0 to infinity part should be there on this, and you close this with some other curve, for example like this. So, but only thing is you have to make sure that on the wherever complex plane you have that may be, so you have to choose depending on what is your integrand of your integral you want to evaluate, you have to choose properly your contour. So, that is the idea. So, you want to, if you want to evaluate certain integrals, certain integral using contour integration, you have to smartly, you have to properly choose your contour in the complex plane and make use of Cauchy residue theorem to get the integral, and the remaining part of the contour. So, the one particular piece of the contour you get what you want, and the other particular pieces you will be able to evaluate, or you will be able to show that goes to 0. Okay. So, that is the idea, basic idea of how to evaluate the contour integration in the complex function theory. So, let me not go into details, many details of this. What we need is we are going to evaluate this integral Bromwich contour to evaluate our Laplace transform f of t, which is 1 by 2 pi I times, and what you have is c minus I infinity to c plus I infinity. This is f bar of s times e power s t ds. S is the complex thing. So, to evaluate this, what we do is this is s is the complex plane, x and y, or the x plus I y is s equal to x plus I y. This is the complex plane, s is a complex variable. So, and you have a c is somewhere here, so that all your f bar of s is analytic this side. This side f bar of s is analytic, where if you have c, that is how you have got this. Okay, where c is bigger than real part of c is or rather real part of s is bigger than c. This is how you have seen, right. C which is bigger than a is the exponential order of exponential of this function f of t. Okay, f is a function of exponential of order a. If f is a function of exponential of order a, you have to choose c such that c is bigger than a, and beyond c you can see that real part of c, beyond c f of s is analytic, because there is nothing singular, everything is there is no singular point on the right hand side. So, f of bar of s is analytic, you can easily see by looking at this that integral f bar of s by definition, that 0 to infinity f of t e power minus s t dt. So, one can show that this is analytic by complex function theory, that this is in the, when you have when you choose real part of s is bigger than c. So, where c is c is bigger than the the function exponential order of f of t. A is the exponential of order A is the order of exponential of f of t, and if you choose c, any c you can choose, and beyond this c, that is the real part of s is greater than c, that means this plane, this half plane, this function f bar of s is analytic. Now, if you are given this f bar of s, you can easily recognize what are its singular points. If you have a singular points, you cannot have many singular points, for example. So, if it is a proper Laplace transform, it will have only some singular points in the finite plane. So, beyond which you will have there is no singular point. So, you can, by looking at this function, you can choose properly, see where this is. This may be some 100 or 1000. If 1000 is if you have 1000 is a singular point, you take see something bigger than 1000 a line. Okay. So, once you choose this, my contour is, I choose my contour like this. So, I break this as I choose, I make a semicircle here, this is of radius r, this is of radius r. Okay. So, if I take actually radius r, for example here, I go like this, semicircle. So, from z equal to at s equal to 0, okay, at x equal to 0, I choose, instead of choosing this this piece which is curvy piece contour, okay, instead of this what I choose is I simply take this line, this is radius r, this is also radius r, but this is not radius r because actual radius is this comes like this, okay, that I am not using. So, I just make straight pieces here both sides. As r goes to infinity, this small piece is going to, let us say if I call this some L, as r goes to infinity, this L goes to 0, as you can easily see, as r becoming steep and steep, it's this is going to be, this L is going to be 0. Okay. Right. So, if your r is here, if you start here, okay, if your r is here and you see that this is your big piece, if your r is very steep, if you take as r goes to infinity, so eventually this is not contribution. So, this we do not care, but we are only looking at this part, and also inside here any singular points this side, left hand side, because you are anyway allowing r goes to infinity, you have to see all the singular points on the left hand side of this line. Okay. So, if you do that, so this is your curve. So, gamma is the curve which is this piece, this semicircular, and this piece and this line. So, you consider like the contour integration, we consider this integral. So, closed part of gamma, this will be f bar of s e power s t ds. This is what I am considering. So, this is equal to over this I break this into actually this piece, that is going to be what exactly that is actually minus c plus I, what exactly is this, this is not IR, right, this is IR c minus IR to c plus IR. As r goes to infinity and I take this r goes to infinity, finally I allow r goes to infinity, this is going to be c minus I infinity to c plus I infinity. So, over this piece, okay, this piece plus over L1 and L2, for example, L1 and L2, L1 union L2, this one as r goes to infinity, this is going to be 0. So, this contribution will be 0, okay, and then plus over this semicircle, let me call this CR, like earlier, if I call this CR, f bar of s e power s t ds. So, this definition, by definition this is actually 2 pi I times all the residues of f bar of s e power s t for this function at s equal to s j, summation from j is from 1 to n, which are sj's are all residue point, singular points on the left hand side of this s equal to real part of s is less than c. So, if this means this left hand side of this straight line. Okay. So, this is exactly what you do. So, and eventually as you can easily see, as r goes to infinity over this line, and you can easily see that e power s t s is real part is negative. So, this side negative part is real. As r goes to infinity, this whole thing is going to be, because of exponential function, whatever may be f bar of s, this is this integral as r goes to infinity is going to be 0, and this contribution, this as such, this will not be there, integral over a null set, because L1 and L2 becomes 0, empty set. Okay. This eventually this becomes a point. Okay. So, this that way this contribution is 0. This contribution I can show because of this e power st, s is the real part, is the negative side. So, as r goes to infinity, so r cos theta is a negative, minus r cos theta t plus I times. So, because of that e power minus r cos theta t, as r goes to infinity, this is going to be 0 as r goes to infinity. Okay. So, this whole thing is going to be 0, this part is going to 0, this part is going to 0. What you left with is only this part, that is exactly your 2 pi I times f of t. This is 2 pi I times f of t by your definition of your inverse Laplace transform. 2 pi goes. Okay. So, what you left is f of t is nothing but f of t is simply you find all the residues for this function in the left hand side of this line x equal to c. So, let us do some example. It is an example how to find Laplace inversion. Okay. So, let me choose the usual which you already know, some example. For example, you already know that what is the Laplace inversion of s by s square plus a square. So, this as a function of t, we know that this is actually cos a t. So, let me show by this general procedure of how do we find this Laplace inversion. So, general procedure is 1 by 2 pi I if you calculate. So, you know what exactly what you get, 1 by 2 pi I c minus I infinity to c plus I infinity, f of z is f bar of s is s square plus a square. This is having, if you look at its singular points, s minus s equal to plus or minus a I. So, a I and a minus a I and plus a I are the singular points for this function. So, I can choose anything any positive c as any c positive as my line, because cos a t is exponential function of order 0. Okay. For that reason I am choosing c as bigger than that is 0. So, you can choose any line like here, and e power st ds. If I calculate this, that is exactly what I need to find, that is actually what is my inverse Laplace transform of s by s square plus a square of t. Okay. This is by definition, but then how do I calculate this? To do this, I have already seen that this is actually 2 pi I times, and this integral is nothing but, we have already seen that this is actually equal to residue of s by s square plus a square e power st, where at s equal to where what are the poles, what are the singular points which are at a I plus residue at s equal to minus a I of the same function s square plus a square e power st. Okay. So, how do I calculate this residue? We have seen this is your function s by s square plus a square e power st. If this is your singular point, you write s minus a I z minus z naught. This is like s is z and singular point is z naught is a I. So, z minus z naught. Now, you take, because it is a simple pole, you can easily see that it is not a pole of order, this is only simple pole, only single pole. So, you have a limit s goes to a I, and similarly here this is a limit s goes to minus a I, s by s square plus a square times e power st times s minus s plus a I, s minus of a minus a I, that is s plus a I. So, what is this one? This is actually limit s goes to a I, and this gets cancelled here some part. So, you have s minus s plus a I, s plus a I, and s minus a I is s square plus a square. So, this gets cancelled here. So, you have left with this, again here limit s goes to minus a I, here also this gets cancelled here. So, you have s minus a I times e power st. You apply now the limit and you see that is ai by 2 ai times e power ait plus this limit will be minus ai divided by minus 2 ai. So, minus minus goes e power minus ait. So, ai by ai goes aa goes here. So, you have 1 by 2 comes out, sum of this half of this is actually 2 cos 80. So, 2 goes, this is exactly cos 80. So, this is exactly what we know already, that this is cos 80. Okay. We will do some more, one more example before we wrap up this finding the inverse Laplace transform. So, for any general Laplace transform f bar of s, if it is given, you look at its where you have to put this line C, depending on by looking at all its singular points. Put them all on the left hand side of this line and choose this contour. You know that this is actually the residues you find the residues of all the poles or singular points of this f bar of s into e power s t, and then you add them up, that is actually your f of t. Okay. So, let me do one more example. Second example is what is the L inversion of s by s square plus a square whole square. If I choose this, if you actually calculate this, you will see that it is by some other means, but if you calculate like 1 by s square plus a square times 1 by s by s square plus a square. Okay. So, you have let me put a here. So, you have 1 by a. So, L inversion of this is same as this. So, you get 1 by a times L inversion of this is Laplace transform of sin a t, and this is Laplace transform of cos a t. So, 1 by a times integral 0 to t sin a tau cos a times t minus tau d tau. So, this is exactly the using convolution theorem I calculated. This you will get as you will see that is going to be t by 2a sin a t. So, I am not calculating, I am just writing directly. This is the result you know already by earlier method. Now, let me use by the general method of finding this. So, what is this one general method of finding this inverse? We have seen that the L inversion of this s by s square plus a square whole square as a function of t, we know that this is actually 1 by 2 pi I times this c minus I infinity to c plus I infinity f bar of s, that is s by s square plus a square whole square e power s t ds. This we know that this is actually all the residues. You look at what are the poles, what are the singular points of this, again ai and minus ai, but it is a pole of order 2 because of square. Okay. It is a pole of order 2. So, you calculate the residues, sum of all the residues. So, we know that this is actually equal to a residue of s by s square plus a square whole square times e power s t at s equal to ai plus residue of s equal to minus ai, but for e power s t by s square plus a square whole square. And as a pole of order 2, this means a limit s goes to ai times what is the, how do you find the residue? If it is a ai is having a pole of order 2. So, I can write like this, like s minus ai whole square s plus ai whole square, this part s square plus a square whole square I can write like this, because of this ai is having a pole of order 2. So, if it is like this, you have to multiply s minus ai square to the function, that is s into e power s t by s minus ai whole square times s plus ai whole square. Okay. I multiplied and I have to differentiate this with respect to ds, there dz. Okay. And I explained that is dz. So, this is what exactly you have to do, and of course, you have 1 by 1 derivative. So, you have 1 factorial. So, if you are doing, if this is m, and if you have a pole of m order m, you have to multiply m, and here you have to differentiate m minus 1 times, okay, with respect to s. Let me not do this. So, m is 1 here. So, because m is 2 here, so the derivative only 1. So, 1 by m minus 1 factorial, I have this, I am using this formula. So, this is 1. So, the same way you can get s goes to minus a I d ds of, now instead of s minus you have s plus a I whole square, and you have s e power s t by s minus a I whole square times s plus a I whole square. So, this gets cancelled both the places, and what is this limit? Limit you differentiate, if you differentiate this and you calculate directly. So, let me write directly, I am not calculating, you can do it yourself, and you see that is going to be t times e power I a t by 4 I a. For this is you will see that is going to be minus t times e power minus I a t by 4 I a. So, if you calculate put it together, you have t by 2 a sin a t. So, this is exactly what you get if you also do it directly also you will get the same answer. So, this is the general procedure of finding Laplace transform, inverse Laplace transform, sorry. So, this is the general way of finding inverse Laplace transform of function f bar of s, which is the Laplace transform of function f of t. General way is through contour integration. So, you need a little bit of complex function theory and its applications. How do you find the how do you evaluate integrals? So, here you do not need really that contour integration technique. So, only thing is how you apply the contour integration technique for this Bromwich contour. If you apply this Bromwich contour here, so you know exactly how to find this what you want this integral, and on the curve part, on the circular part, as r goes to infinity, you can show that is going to be 0 because of a negative side, it is negative real part, okay. S is negative real part. So, e power s t an exponential function of negative real part of negative real part. So, that is e power minus real part of s into t. So, as r goes to infinity, that is going to be, as r goes to infinity, negative part is becoming bigger and bigger. So, that makes it that integral 0. So, you end up seeing that finally the required integral is simply sum of all the residues on the left side of this line, c minus I infinity to c plus I infinity. So, you just need to calculate the residues. How do you find the residue value, residue of a function which are at poles or poles of order m? Usually you see, if it is required, if you look at some functions, you can expand, if you should know how to find, it is a Lorentz series expansion or a Taylor series expansion. If it is usually you end up getting some elementary functions, whatever may be working, you are working with some function, it will be composition of elementary functions. So, you can expand all of them together, and you see that you can get Lorentz series expansion, and in that the coefficient of 1 by z minus z naught, if z naught is a singular point, that is your residue. So, if it is a pole of order, you have the formulas to find the residue, otherwise you have to expand its Lorentz series expansion, and look at its coefficient of 1 by z minus z naught, okay. So, that is how you find this, you only find the residues and you add them up, you end up getting inverse Laplace transform of a function, okay, f bar of s, that is f of t. So, this is how you find these inverse Laplace transforms. You have seen so far how to calculate inverse Laplace transform of in a different ways. If it is a simpler functions, you can use partial fractions, convolution theorem you can apply Heaviside expansion theorem, and also it looks like Heaviside expansion, but if it is a kind of series, it is not because of the Heaviside expansion, but by general form, that is a fourth type, that is finding using the inverse transform definition, that is using Bromwich contour, complex function theory, contour integration, you can apply and get the inverse transform as a sum of all the residues. That will give you kind of as though you are applying Heaviside expansion theorem for the Heaviside series, okay. We have seen some example like when you have instead of taking polynomials you have a cos hyperbolic function and sin cos hyperbolic functions you have chosen, and for which you have seen what are its poles. So, they are simple poles that works only if it is a simple pole. Okay. It looks like Heaviside expansion theorem as though you applied without bothering whether they are finite or not in that example that we have seen in the earlier video. Is actually that's it looks like Heaviside expansion as though you simply applied only if your function is having a poles which are simple poles. If you have poles of order some other order higher than 1, then that will not work. So, it will be looking different. So, in any case a general way of finding the inverse transform, that is by contour integration, is finding all the residues of the function f bar of s into e power st, that is your function, complex function, for which you look at its residues for which at all the poles of that function, and then you calculate its residue and sum it up, you end up getting inverse transform. So, we will see Laplace transform, you know now how to find the Laplace transform and inverse transform. We will see the applications of these Laplace transforms. For example, start with ordinary differential equations and ending up solving some boundary value problems for the partial differential equations, and also for integral equations, how do we solve certain type of integral equations. We will see that in the next 1 or 2 videos. Thank you very much.